In this video, we're going to continue talking about Chapter 4. More specifically, we're going to begin to talk about our second batch of measures, which are measures of dispersion. So, what we are trying to find out with our measures of dispersion is how spread out is our data. And an underlying concept behind that is how consistent is our data, how reliable is what we are getting from this going to be. We're going to talk more about that as we go along, all right? But these are our measures of dispersion. We're going to start by just talking about some very basic ones. All right, the simplest one is the range, right? So the range is an example of a measure of dispersion. We probably remember this from grade school when we were going over things like the mean, median, and mode. We're not going to do a lot with the range. Actually, we're going to do very little, but it is helpful because it's something that most, if not all of us, are familiar with to help illustrate that the concept of a measure of dispersion. All right, so let's take our data set that we had been using, or I'll just throw one in here. So if any of us remember from that, the data that we were using for our measures of central location stuff, right? Our maximum value was 1017. Our minimum value was 19. So if we were to take the range, right, we would of course do 1017 minus 19, which would give us 998. All right, so that's telling us that the smallest value and the largest value, that's how far apart they are, right? The larger that number, the more dispersion, the more spread out our data is, right? Because our data can go from anywhere from 19 to 1017, right? Now, the range is not a very sophisticated measure of dispersion because, well, we don't know where, how many values are closer to 19, how many are closer to 1017, right? We don't know any information like that. It's just telling us one end to the other, what's the range of the data, or how far out does that data go, right? But again, the bigger that number, the more dispersion, the more spread out, presumably, the data is going to be, especially if you're just looking at it on a basis of range. Right, but we are going to be using, and that's essentially all we're going to do with the range. Again, we're not going to spend a lot of time on it. We are going to we're going to look at a more sophisticated measure of dispersion. And this measure of dispersion, right, this along with some other ones, so we're really just going to look at the kind of the most commonly used one, but there are some other ones that focus on this idea of deviation from the mean. All right, so what is that? All right, so the deviation from the mean is the difference between an observation and the mean, right? Mathematically, we would write it something like this, all right? So this would be kind of expressing the population side of it, but x, so that is our observation, right? And then, of course, mu is our population mean. So our deviation from the mean, again, simply just that difference between our observations and the mean itself, right? This is written here as the population mean. We can also do this for the sample mean. Right, so in your book, I believe they mention one way of doing, well, actually, we don't necessarily, so one way that this is used is the mean absolute deviation, something like that. It might have more letters in there, I don't remember. But that's one method of calculating kind of a measure of dispersion. What we're going to focus on, however, is the variance, all right? So the variance is the average squared deviation from the mean. Right, it is based on this kind of concept of deviation from the mean. And there are two types, as we saw with our mean, right? We've got two kind of formulas for essentially the same thing, right? Depending on whether we're dealing with population data, so a parameter, or if we're working with sample data, which would make us be dealing with a statistic, right? So the population variance, so this is the one that, so this is the parameter value, right? The population variance is, actually, you know what? We're gonna just do that so I don't run out of space. All right, so this is, oh, I'll write this up here again. So population variance. All right, this symbol that we've got here, all right, that is sigma squared. All right, and that is how we notate the population variance. In our numerator, we're going to have the sum of xi minus mu squared divided by n. All right, so if we remember, n, capital N, that's our population size. So just however, if we have population data, how many data points do we have? Because that's going to be the total number of the population, right? So it's going to work just like any of those other ones would. Right, so this is our population variance. Now this formula looks a little bit daunting. It's not that bad, although it does not look great. One thing I do want us to focus in here before we actually, maybe we'll wait on that. All right, so that is the population variance. We're going to go ahead and look at the sample variance next, and then we'll work through some examples. Or actually, we might look at some other stuff and then work through some examples. All right, so that was the population variance. The sample variance, it's very similar, but it is not the same. All right. So when we were looking at our population mean versus our sample mean, the only difference was in notation. There was really no difference in the way you calculated the mean, whether it's population or sample. That is not the case with the variances, right? There's a small but important reason why they are different, and it is important to know that difference. And identify when you should be doing the sample variance versus the population variance. All right, so there are some differences in notation, right? So instead of using, oh no, what did I just do? Okay, ooh. So instead of using the mu, all right, we've got x bar here, so in our numerator, sum of xi minus x bar squared. That is essentially, operationally, that's going to be done the exact same way as with the population variance. The big difference comes here in the numerator, where instead of the sample, or the number of observations we have, right, we're dividing by n minus 1. So the sample size minus 1, so just however many pieces of data we have minus 1. Right. We're not going to really get into why we do this. I'll mention something about it here in a second when we start looking at an example. But for now, let's just know that that is something that we do have to do. All right. So that's the sample variance. There's not really a whole lot more to say about that. So I guess we. All right, so one more thing before we look at an example. All right. Oh, wait, no. There was something. Okay. So with our formulas, and I'm just going to do the population up here. All right, so here is our let's see if we can make that well. Anyways, well, all right. Our numerator. I'll just do it this way so I don't. All right. So in our numerator, we see that we're taking that deviation from the mean. All right. So that deviation from the mean, xi minus mu. All right, and then we're squaring that. I want us to talk a little bit about why that's the case, partially just because it's something I like doing. But so why are we squaring that? Right? Why don't we just add up our deviations from the mean? So why isn't it just the sum of xi minus mu? Right, and the reason for this is what we're about to look at. This is not necessarily something that you're going to have to memorize or write down for the test, but it is something kind of worth noting and to help us try to avoid some things in the future. All right, so when we are taking these sums, we can break this apart a little bit. So we can distribute that sum so that we have the sum of xi minus the sum of mu. Right, so then we're going to take that sum of xi, and then we're going to expand mu. Right, we know that mu is the sum of xi over n. Right, then if we add up this term, right? So essentially we've got however many observations, that's how many times we're going to be. Actually, let's make this a little bit more specific. So technically speaking, for these up here, right? We're going to throw in some of that notation that we aren't necessarily going to worry about later on, right? But what we have here is the sum from I equals 1 to capital N for all of this. All right, so essentially we've got, capital N distinct xi's, right? And so we do kind of notate that with that I, so we know that we're getting it in there, right? It's not always as obvious to know that we're doing the same thing, right? The same thing applies, right? I equals 1 through n. Even though we don't have any I there, we are still doing this n times, right? So we're adding up mu n times. So I'm going to drop that notation, right? So when we expand it, actually we might bring it back, all right, for this one. All right, so when we expand that mu to the formula for mu, sigma, the sum of xi over n, right, we're still adding that up, we're still adding it together n times, right? There's nothing really variable in here, so when we do that, we're going to end up with the sum of xi minus, right, well, if you add up this term n times, right? Sum of xi over n plus sum of xi over n plus so on and so on until you've done that n times, then you're going to be left with n times the sum of xi over n. Those n's are going to cancel out, and then you're going to be left with xi minus the sum of xi minus the sum of xi, which is going to give you 0. All right, so that's a very long way of saying that we need to have that square, right? We need to square these differences, because if we don't, if we forget to, when we go to add up all of our deviations from the mean, they're all going to cancel out, and we're going to get 0. And that would mean everything would have a variance of 0, right? So that wouldn't be very informative. Right. The other thing that I'd mentioned from your book, the mean absolute deviation, they get around this by taking the absolute deviation, or excuse me, the absolute value of that deviation from the mean. All right. So again, you got to have some way of making sure that those deviations from the mean do not cancel each other out. All right. Then the last thing before we actually look at an example, finally, is standard deviation. All right, so standard deviation is another measure of dispersion. Follows closely on the heels of variance, and the reason for that is because it's simply the square root of the variance. All right, that is how we are going to calculate it. All right, so when we're looking at the population standard deviation, the formula is sigma equals the square root of sigma squared, right? For the sample standard deviation, it's just going to be S equals the square root of S squared. All right, pretty straightforward. The standard deviation we're going to be dealing with quite a bit. In a lot of ways, we're going to be dealing with the standard deviation more than we will with the variance. The standard deviation has a lot of desirable properties. Probably the biggest one is that it's more easily interpreted than the variance. And again, we're going to look at that as with a lot of these things here in just a second when we start going through an example. All right, but that is it. Standard deviation, it's the standard amount of deviation from the mean, right? It's going to just as a general, how close to the mean do we expect most observations of whatever data we were looking at, right? How close do we expect those to be, right? Within how much, right? So let's go ahead and take a look at this. All right, so this is going to be our let's see. So I asked my siblings how many pairs of shoes they own. All right, and this is actually true. I just did this. All right, and found the following results. All right, so I have 4 siblings. I also included myself in this list. All right, so some differences there. All right, and so I want to know. Let's say that I'm only interested in my siblings. All right, so that's my population of interest. Right, I guess technically I should say my parents' children. So that way I am included as well. All right. All right, so if that's all I'm interested in, Right, the reason this is important is because we have to determine, should we calculate, and ultimately we're calculating the variance, right? So we need to figure out, are we going to use the formula for the population variance, or are we going to use the formula for the sample variance? Right, so if we are only interested, I'm going to go ahead and erase this, we don't necessarily need to keep that there. All right, if we are only interested, or if I'm only interested in my parents' children, so my siblings and myself, right? Well, then we should use the population variance, right? Because I have 4 siblings, and then myself included is 5, right? There are 5 data points here, all right? So we have the data for the entire population we're interested in, right? So we are going to be using this formula, so sigma squared equals sum of xi minus mu squared divided by n. All right, so one of the first things that we need to do is we need to find mu. All right, we need to find that average. All right, so we're not going to spend any time at all on this, really. We've already gone over averages, right? So to find the population mean, right, we have all the population data over here. All right, so we just need to add all of that up, divide by 5, which is the total number, the population size, and we would see that we get a mean of 21.2. All right, we're going to erase some of this stuff. I guess that really was not the stuff that really needed to be erased, but that's okay. All right, and I'm just going to pop this over here. All right, so mu equals 21.2. Give ourselves a little bit more space on the screen. All right, actually, I'm going to get rid of that too. All right, I'm going to put that over here. All right, so when we are doing this, especially when we're first getting started, something that we're going to want to do is find, essentially, we're just going to go through this step by step. All right, we're going to do a series of kind of calculations, a series of columns, and we are just going to start by finding that deviation from the mean. All right, so this first one, we've got 15 minus 21.2. That is going to give us 6.2. 32 minus 21.2 is going to give us, let's see, 10.8. 25 minus 21.2 is going to give us 3.8. 8 minus 21.2 is going to give us negative 13.2. And I made a mistake up here. This first one, 15 minus 21.2, that should be negative 6.2, not just 6.2. All right, and then finally 26 minus 21.2, that is going to give us 4.8. All right, once we have that, we are going to want to square those values. I'm going to give you guys a little bit of time to write those down so we can clear this off. All right, or I can clear this away and just keep those values. All right, or I guess you could just pause if you haven't gotten them yet. So that's what we're going to do. All right, so now we're just squaring all of these values. right, these deviations from the mean. Right, so once we do that, we're going to get this 38.44, 116.64, 14.44, 174.24, and then finally 23.04. All right, once we have all of these values, all right, we are going to these squared deviations from the mean. All right, we're simply going to add them all together, right? And we're going to get 366.8. All right, once we have done this, all right, we're essentially done, all right? Because this is what is in our numerator here. Right, and so now we just got to divide by the population size. All right, so 366.8 divided by the population size, which is 5, is going to give us a variance of 73.36. All right, before we move any further, doing this calculation this way, here I did it out kind of more than I normally would. You could, especially if you had a sample or a population size of 5, all right, that's a pretty small. If you've got a small number of observations, you could do these variance calculations in your computer without having to write any of this stuff out. However, when we're first learning how to do this, it is, it's not terribly complicated, but especially the first time you see it and the first couple times you do these calculations, it can be a little confusing. So doing these step at a time, and you don't have to do every single step that I did, writing them all out, but using that step method, it can help you identify where you make mistakes. So if you, if you answer a question on the homework or on one of the Hawks things, and you're not sure why you got it wrong, you can go back and look and see. Sometimes you just forgot to square something, sometimes you just wrote something down wrong, and it'll help you go back and check that work. All right. Also, just kind of helps kind of flow through these things, all right, and not have to, you can simplify things quite a bit, all right. But again, you don't have to do it that way, but it is a very helpful way to do it. All right, so I'm gonna just erase this. All right, I'm gonna put up some information. So we've got our mean, 21.2. We just found out our variance, which was 73.36. And then if we wanted to find our standard deviation, right, we could take the square root of that 73.6 to get 8.565. All right, so looking at this information, we see, all right, we've got our mean, right? So the average number of pairs of shoes owned by me and my siblings is 21.2 pairs of shoes. All right, so that's not necessarily an interpretation, it's more of just stating a fact, all right? So that's how what that is telling us, right? The average number is 21.2 pairs. All right, then moving on to our variance. All right, we'd say our variance is 73.36. All right, but one thing to note, I'm going to move some stuff around here real quick. One thing to note with our variance is that when we do our variance calculations, we're squaring all of that stuff, so we're also squaring all of the units of measure. Right, so we're never going to really write this out, but technically this is 73.36 pairs of shoes squared, right? So I don't know personally what a pair of shoes squared is. That's not really something that's very easy to interpret. And so while the variance is a good number to have, we really more want the standard deviation, right? Because once we take the square root of all of this, right, those squares cancel out. This 73.36 becomes that 8.65, right? So our variance, our standard deviation rather, our standard deviation has the same units as our mean, right? So 8.565 pairs of shoes. All right, so we're not squaring that unit of measure, right, we're leaving it as it is. All right, so when we go to interpret this or kind of just state what it's telling us, we could state something along these lines, right? Let's see. I would expect the number of shoes me and my siblings own to be within 8.565 pairs of shoes. Let's see, that's a bad way of writing that. I would expect the number of shoes. No, that's garbage. Well, another way of saying that would be, I would expect if I randomly selected one of my siblings, I would expect that the number of pairs of shoes they own to be within 8.565 of that 2.21 or 2.21.2. See, this is why we write things out. I would expect, we're going to try this again, the number of pairs of shoes owned by one of my siblings to be within 8.565 of 21.2 pairs of shoes. All right, that's a better way of writing that out. All right, so we're going to talk more about standard deviation and all of that in the chapters to come. But for right now, we're going to kind of leave it at that. Again, it's a standard deviation, so kind of most, especially depending on what distribution, which we haven't gotten to that kind of stuff yet, but depending on which type of distribution that it's affected by, it's very likely that you're going to be within one standard deviation of that mean. All right, so just very quickly, let's say, and then we'll wrap this up. So let's say that we had that same data, all right? I'm going to write it back up here just so we have it. All right, no, that's not that. So, but let's say that instead of my population of interest, right, the group I'm interested in, instead of that being me and my siblings, right, maybe this time I should say everyone, right? So just kind of all people. We're trying to figure out kind of what the average amount of average number of pairs of shoes people own or what have you, right? How would that change what we are doing? Let's stop writing in that blue, right? And the answer is it doesn't change it too much, right? The biggest thing is that now, instead of using the population variance, we need to use the sample variance. Right? The reason for that is because everyone, so one, we can look at our data, all right? We have 5 observations, right? So 5 observations, all right? If we're looking at everyone, right? Are there only 5 people included in that everyone? No, all right? So the population size does not equal 5, right? So that tells us that we've got a subset of the population, right? Because we don't have data for everyone, right? We have data for me and my siblings, all right? And so we are going to be using the sample variance, right? So most of this is just like what we did a second ago with the population. There are some small differences though. All right, one, we're going to need to find the mean, so this time it's the sample mean. And again, with our means, the way we do the calculations for the way it works for the population and for the variance, the way it works for the population and the sample, right, essentially identical, right? So the mean is the mean. We're going to calculate it the exact same way. It's going to be that, well, I didn't even write it down, but whatever we add up, I thought I wrote that down somewhere. Maybe not. But what would that be? 106 divided by 5 or whatever it was, right? It's going to be the same numbers, right? So we're going to get that same 21.2. And when we go to find our xi minus x bar squared, that's going to be the same too, right? Because x bar is 21.2 in this. The xi, right, is the same numbers that we used last time, right? And so I'm just doing this to save a little bit of time. If this was a different set of numbers, we would of course have to actually do this calculation again. All right. But as it stands, all right, the only thing we're really changing is this last little step, right? Because instead of 366.8 being divided by 5, it is instead divided by 5 minus 1, or 4. All right, and that gives us 91.7, all right, as our variance, right? So really the biggest thing, kind of most students have most students get catch on pretty quick on the actual computations, right? But this part, all right, this knowing when to divide by n minus 1 and when to divide by n, right? That's one of the trickier things, right? And that comes down to the stuff we were doing in the first chapter, right? Identifying when you have a population versus when you have population data versus when you have sample data, right? And then one of the last things, of course, if we wanted to find our standard deviation, right, we would take the square root of that 91.7, and that would be our sample standard deviation. All right, so when we're looking at these, all right, so we're just going to quickly compare the sample and the population numbers. All right. So, like I said, those means are the same, right? You really don't change how you calculate that mean. All right. So again, these are from the same numbers, right? Only difference is one is for one is the parameters, and one is the statistics. All right, so again, we're not really going to talk too much about the importance of being able to identify that. We've talked about that enough. What I do want to point out is notice, all right, the ones that are different. So our actual variances and our standard deviations. All right, so again, the same numbers, essentially the same questions. The only thing we're really changing is whether it's a statistic or a parameter, right? And we notice that hopefully we notice that these sample measures are higher than when compared to the population ones. All right, the reason for that is because when we are doing that population variance calculation, we divide by n, so the total number of observations that we have, right? When we are doing our statistics, we divide by n minus 1. All right, so this is why we do this. All right, when we have population, right? When we're looking at a parameter, we're looking at a population, we have all of the data for it, right? So we have all of the pertinent information to calculate the variance, standard deviation, and so on. But when we go to the statistics, right, when we get sample data and we're calculating the statistics, right, we don't have all of the pertinent information, right? We only have a subset of it, right? And so that's why we divide, or that's why we subtract 1, right, from n when we are dividing, right? Essentially, this is a penalty, right, that's going to make our variances larger, right? Because not only, I guess this is something I haven't necessarily mentioned that much. So the variance and standard deviation, this is a measure of dispersion, but one of the things that we're going to look at it for most often is for an idea of kind of certainty, risk, right? How much, really looking at to see, can we make estimates based off the information we have? How close are we going to get to those estimates? All right, how accurate are we going to be? All right, what's the likelihood that we're going to have just something way different than we expect? So kind of this idea of taking into account randomness and chance in these numbers, right? And so because we don't have as much information for these statistics, right, then we need to penalize ourselves, right? So we don't have full information, so the uncertainty is even higher, right? Because there's pieces of information out there I don't know, right? And so we penalize ourselves, we subtract that 1, right, do n minus 1 divided by that, right, and that brings up our standard deviations and our variances. All right, but that is it for this section for the measures of dispersion. That's it. There's only one more section in this chapter to go over, and that is going to be we're still in chapter 4. All right, we're going to be looking at measures of relative position next. All right, but that is it for this video, and I'll see you guys in the next one.